Over here, nearly obscured by all the light from the object, is the relationship between the frequency and wavelength of light, right? C being the wavelength of light, 2.9998 or something like that, times 10 to the 8th meters per second. I'd solve Maxwell's equations in my head, but I don't know the constants of that. No, I can't solve Maxwell's equations in my head. Okay, right? That comes from Maxwell's equations, which is kind of the underlying idea behind relativity, which we're going to talk about a little bit, but not right now. Okay, anyhow, and you know that the energy is h times f, where h is Planck's constant. If you don't know that, no, you don't remember it from when you did. Okay, momentum of a photon is its energy divided by the wavelength, by the speed of light. Okay, using these ideas, and here's Planck's constant, very approximate, 6.64. After that, we'll call it 6.7, and that's real close to 3. Okay, so now we have an enclosed reflecting cylinder. Okay, we have a single photon in this cylinder. Okay, what's the average pressure in the cylinder?
Not a lot.
Yeah, it wouldn't be a lot from a single photon. We can calculate it.
Doesn't it matter on the dimensions, like
How big
the height versus the circumference?
No, but you can assume it's a cube if you want, but only the volume really is related for the same reason the kinetic theory leads to PV equals nRT for molecules.
Do
So
we
just
know
assume it's
the
a cube.
wavelength?
Yeah, assuming you know the wavelength or the frequency. Now we can measure the wavelength. So take the photons that come out of that laser. You've measured what you need to, the diffraction grating and so forth. So you know how to get the wavelength, right?
All you need to know is the momentum, right?
Yeah.
It would
So
be
this is
H.
straightforward. If you know the wavelength, then find the momentum. So now you know the momentum of this photon. What else do you know?
You need to know how many times it hits the walls per second.
You know that because you know the speed of light.
Yeah.
But how do you know at what angle it's traveling? Because
Well, you're going to have to figure that out for kinetic theory.
depending on the angle,
Depending on the angle, you have unequal forces in these. So I'm saying the average pressure, average the pressure over the
like
6 walls.
if it would be going from corner to corner, it would take longer, and so it would cause less pressure than if it were going from.
Yeah, you're going to have less pressure on these than you will on these, if those accurately
Yeah.
represent this. But you can still average the pressure. And then, and of course, the real question is, if you've got a bunch of photons in here, a whole bunch of photons, then their directions are pretty random. Now, they're not bouncing off of each other. Matter of fact, there's just an article today where they actually caught light interacting with light. I think it might be the first time they've been able to observe that. They're coming up with some pretty good stuff. Okay? They never asked me how to do it. Okay.
They managed to collide 2 light particles.
They saw evidence of collision of 2 photons, or whatever they are. Okay?
What happened?
I don't know, I didn't read it. I woke up at 1:45 this morning. I finally got back to sleep about 6 a.m. after trying to do some stuff and not being able to think. Finally got sleepy and slept for an hour and a half, so I'm okay now. But that's when I saw the article. There was no point in me reading the article. I don't even remember what I did during that time, but hopefully none of it was illegal. Okay, now, or if it was, hopefully it wasn't harmful, right? Okay, so, you just assume that you've got a large number of photons, or assume that the walls of this thing aren't perfectly parallel, right? So the reflections are going to come off at different angles every time, so you just have a mix of directions so that your question becomes irrelevant, okay? And you just do the same derivation. You could start, as we did, just assuming that the photon just goes back and forth between 2 walls, okay? and you get the change in momentum. It's going to be 2 times this, and it's moving at the speed of light, so it's going to collide a lot of times, right? Okay? And then you can do, as we did with the first model, where you just say, okay, if we randomize this thing, then we're going to get 1/3 of that force, that momentum change, that average force. Okay? If you remember that argument that we made back in January. Yeah, well, not going to review it. Okay. So, single photon pressure and all that stuff. Now, the interesting thing about this is now, and this is not a problem I would ask you to do, but you actually could, because I saw this problem first when I took a graduate level electromagnetism course after I started working here. Okay? And in that course, I took the standard graduate text and just worked all the problems. Okay? And did that. There's only one problem I couldn't do, so I'll put that on the exam. Very simple. Question is, what if gravitational force was 1 over r to the 2 plus delta, where delta is any tiny number? Why would the universe become unstable? My professor couldn't solve it either. So, you know, when I retire and can think clearly, I've got to solve that problem. It's the one problem of Panofsky and Phillips that I couldn't solve.
So
Neither could the professor.
So stable orbits couldn't exist?
Yeah, stable orbits couldn't exist. But prove it. Might have to use Gauss's law. Be a place to start. I tried that. I'm thinking more clearly now. Because then I was too young to think clearly. How old was I? I wasn't 30 then. So I was still stupid, but now I'm real smart. Yeah, you're supposed to laugh. Okay. You can guffaw if you like. Okay, so yeah, my whole point here is, you can now do thermodynamics with a gas that consists of photons. And you can imagine expanding and contracting this cylinder. Okay? And this problem I didn't find particularly difficult at the time. Just thought about it for a little while. First of all, it kind of blew my mind to think of a photon gas. Okay? Never thought of such a thing before. But once I did, I said, okay, well, you got the momentum relationships. I know how kinetic theory works. So you just do it. And you derive this, which is relevant to our attempt to get that aluminum strip across the rails of our purported railgun to actually deflect due to the current in the loop. Okay? Because if you put enough current in it, you should definitely get a deflection. But if you put too much current in it, you're going to melt or explode the aluminum strip because it's very thin. Of course, we use it because it's very thin and deflects very easily. So that's kind of neat. So obviously, there's a connection between this and that, right? No, it's not obvious. Okay? A connection between this and that is the rate at which energy is radiated from an object is equal to E sigma T to the 4th, T being absolute temperature, E being emissivity, a number between 0 and 1. A perfect reflector doesn't emit anything. It just reflects everything. So inside of this is a perfect reflector. Its emissivity would be 0. Human skin has a high emissivity, and pigmentation doesn't make much difference. Okay? Yeah, emissivity is over 0.9, so almost over 90% of the sunlight that hits you gets absorbed. And over 90% of the energy that gets to the surface gets radiated. okay? That's not really an accurate statement, but you can still kind of use it. T is just Kelvin temperature, the absolute temperature. And sigma is a constant that you derive by doing the thermodynamics on a photon gas in a perfectly reflecting cylinder. Okay? Now that's actually kind of a graduate level question, although a good undergraduate can do it, but I'm not going to ask you to do that. But it's a neat connection, so since it came up, I thought I would do it. Now, what I would do in the illustration here is, I would in some sense feel free to ask a question like this in the final, to see how far you could get with it. And I would certainly expect you to understand that you have a momentum exchange on the collisions and try to at least quantify that, right? Okay? And I wouldn't necessarily expect you to get all that far because it's a little esoteric. But you're going to expect to see questions that require you to use the kind of thinking that you need to use to understand things we talked about. It's one of the things I'm trying to get you all to do rather than following a bunch of formulas. Think through things, okay? So I want to see some evidence that that's happened, and I see it all the time. I think you've done pretty well with that, which is a good thing because you haven't handed in that many problems, which worries me a little, okay? But you did well in the midterm, so I think there's hope for you, but you've got only 2 weeks from today to make that hope come true. Okay?
And
No.
then we graduate.
Huh?
And then we graduate.
Yep.
Some of us.
Well,
Some of you might graduate. I don't know about you.
I guess.
Oh.
I guess just me.
You need this course, right? Yeah, well, I know you're going to pass.
Oh yeah, I can pass.
Try to
with a D.
avoid the D minus thing, though. Okay. Okay. Other things you really need to know is
the
the
turn in your file exam, just gonna be one piece. of
geometry,
paper
the
that
ray
says
tracing.
no,
It's on that board right
whatever
there.
grade.
Haven't erased it. Principles. Can you take the principles, put them together, and make at least some conjecture on an impossible problem? Okay?
Those are
Make some kind of
frustrating.
progress. What can you think of? Huh?
Those are frustrating after 2 hours in the test.
True.
Well, put them at the beginning then so you don't have time to do anything else.
Okay.
Yeah, I don't know exactly what I'm going to do with that. I'm seeing all kinds of articles, and every time I read an article, I think, hey, these guys should understand that. Another one. To heat up a plasma at 100 million Fahrenheit, Kelvin, so you get nuclear fusion, okay? You have a beam of plasma, and you contract that beam with a magnetic field. What happens when you contract things? A plasma basically kind of like a gas. When you contract a gas, it heats up, right? Kind of a neat idea. Call it the Z-pinch. There are details of it. I just scanned the article. But that's the kind of thing I could ask you, okay, how would you orient the magnetic field to do that? If you know the right-hand rule, you can figure it out, right? If you don't get it right, at least you tried to use the right-hand rule and did some thinking, and I can give you some credit for that, right? Make sense? I'm not expecting miracles. Now, most of the tests will just be problems. You know, not problems in that level, but I'm thinking in terms of maybe putting a few of those and say, read these and see which one you think you can do and do something with them. Thinking from principles, okay? Actually, I've got this thing on. If I didn't say anything, it'll get me in trouble.